Okay, it worked. It worked. All right. There we go. Press F in the chat for Trenton and Emily and Julia, who are going. And Emma, who's been gone every day. But okay. I guess I should say what I said earlier for all the Twitch followers. So because the AP tests are next week, we're going to cover the last bit of material. It's like 2 short problem sets. I'm going to cover the material from the first one, like today and tomorrow, and then Wednesday, Thursday, we'll cover the gravitational fields and orbits, and then we'll have time after AP test week to just finish them up, and then we'll take quizzes on them. So, but anyway, I'm gonna cover them in class before the AP test, so that you at least you know the ideas. Okay, first thing.
Is the AP test just multiple choice, or is there a writing question?
There's a free response. It's a combination, multiple choice and free response.
That's right.
What?
That can't be it. That's all.
What? What do you say? What do you
I
say?
don't want to have to do free response questions.
What? I cannot understand what you're saying. I'm sorry.
I don't want to have to do the free response. So can I skip that?
Yeah, just skip that. Yeah.
Okay.
I think you get a 5 if you just skip that. They just give you full credit.
Right, poggers on.
Yeah.
Anyway,
Just right,
I won't
yeah.
have to do that.
Just put some Kekwoos on there. You'll be good to go, I think. Okay. So the first thing to discuss is a wave. So I got a bunch of simulations for you today.
Oh,
That I guess I'll try to. This first one. So read this first question here. It should be pretty self-explanatory as far as like what it's describing. What? So, yeah, it's a bunch of stuff to talk about with waves. So, we all know we've all heard of a wave, right?
Yeah.
So, when a wave travels through space, get some vocabulary out of the way. So this says this diagram shows a snapshot of a wave on a string. So it could be, so imagine I can show you one on this coil over here if you want, but because it's fixed at one end, it's going to bounce off. Here.
let's do it.
You have to use your imagination to see what would happen if this string was just infinitely long. Here's the string. If I take my hand and move it up and down, I can actually get, this is what we'll cover soon, the standing wave. Okay, but let me just stop it here. If I just send one pulse down the wave, you had to look pretty quick there to see that first pulse. So there's a whole bunch of stuff we're going to talk about here, which is this pulse. It bounced back. There's a reflection of pulses, but
That's pretty neat.
yeah, the standing waves are really neat. I think those are always fun to discuss. They're cool looking, and then they're interesting to describe mathematically. So, oh, actually, you know what? I was going to show you this one first. I don't know. I'm gonna post these Desmos files, so if you want to look at them, I'm sure it's going to be hard to see from this angle, but so if I run this simulation, there's a lot of stuff to look at. Do you see how the wave is traveling to the right pretty slowly? But if you put your attention on like one dot, just pick one dot, each dot is just moving up and down. You see that? So that's the first element of a wave, is like, what?
Would it be fair to say that almost like a helix, just like digitally?
Oh, I mean, it looks a little bit like, yeah, like a rotating helix, but that's not really,
It is like an optical.
yeah, it's more of an illusion.
And
There's another one here.
Oh, I thought that's the path.
What?
Path, PHAT path.
No. So when you make a wave, I'm going to make this and so imagine an infinitely long string. If I disturb this,
oh, that's so.
I'll post all these on Classroom. You can look at them if you want. So now this is me trying my very best to oscillate the string, and you can kind of see the wave. My hand is not steady enough, I guess. So if I go, I wanted to oscillate.
Oh.
So if you take this and just go up and down, like look at the sine wave. You see it?
Yeah.
Now, if you look at a peak, you can be like, oh, it's moving so fast. That's the wave speed. But again, look at any individual point. Let me slow-mo it. Like, look at this dot. It's just going up and down, up and down. So this is called a transverse wave. So any point on the string is just going up or down. But as a whole, it looks like these peaks are moving and transferring energy. So anyway, any questions on that? General idea first? No? Okay. So there's a lot of stuff to talk about then with the shape of that wave. So let's say you take a snapshot of the wave. And okay, it's got this shape to it. The first question you ask is, well, how long is it? How long is one single wave? What word do you think they use to describe the length of one wave?
Wavelength.
Wavelength. Yes. So this is the wavelength. Okay. So this is the symbol that's used to describe it. Does anyone know what that symbol is called? Lambda. Lambda. Wait a second, is there a B in lambda? I can't remember. I don't think so. Maybe there is. You know when you write something and you're like, wait a second, is that how you spell that? There is a B in lambda. Okay, sorry. Lambda. Lamb, like lamb chop. You guys remember lamb chop? No.
No.
They sang the song that never ends.
Oh.
This is the song that never ends. It goes on and on, my friends. No? Okay, never mind, guys.
Not the never-ending song.
I know the never ending song.
So, by the way, do you understand that this length, so the length of one oscillation, is identical if I went like this, peak to peak, for example, or valley to valley. Sorry, valley to valley. Do we understand that or no? Are there any questions? It might not be a super obvious fact, but just shift this measurement over. So that's one way you'll typically measure it is look at the distance between two peaks. That's one wavelength, one full oscillation. Okay. What else would you want to look at here? Well, you'd want to look at, well, how fast are these peaks moving? What's the wave speed? No. Can't be hertz, right? Because hertz is the measurement of, what's the word? Frequency. So it can't be speed if it's frequency. Those aren't the same thing, right? So wave speed, let's call that V. But that's the units here. So what's going to be the units of wavelength?
Lamb chops.
Lamb chops, yeah.
Per second.
Meters. No, how do you measure length? Meters. Right? What's the units of speed? Meters per second. And then, if you look at the question, there's this thing about frequency. Now, frequency is like, go back to this animation. If I go to normal, notice there is a frequency here, 1.5 hertz. So where is the frequency on the wave? You can't really see the frequency from looking at a snapshot. You'd have to look at one of these points, say the thing generating the wave, and go, well, how many oscillations per second? If I turn this down, if I turn it up to 2, it's doing now 2 full oscillations per second, right? If I turn it up to 3, now it's doing 3 oscillations per second. Notice what happens when you turn up the frequency.
It looks wild.
Good. It's traveling faster.
That's
Well, there's a lot of things going on here. Let's say I turn the frequency to 1. Close enough. Now it's doing 1 oscillation per second. Notice the waves are farther apart, right? Okay, so, and then the last property here is frequency. So frequency is, we still use F. And of course, the units of frequency are hertz. Okay, so there's our markers. Not doing too good. Where's my extra markers? So what's the relationship then between all these things? I'm just going to write it here. It's really simple formula. So why does that relationship hold? Why does that make sense? Well, what does wavelength tell you? Wavelength tells you how many meters are in one wave. That makes sense? Or one cycle. Okay. The frequency tells you the number of waves per second. Does that make sense? So for example, if the frequency was 5 hertz, that means 5 oscillations per second, meaning 5 waves are generated every second. Right, like on this animation. If this thing spins around 5 times in a second, you would be getting 5 full waves during each second. So if you multiply how many meters per wave multiplied by the number of waves each second, well, with the units, that would give you the number of meters per second that the waves are traveling. Cool beans? Simple? Easy peasy? So answer the first question then. In this question it says, I missed one piece of vocabulary. You guys see the one I missed? Amplitude. So there's going to be like a baseline. The amplitude is this distance here. Okay, amplitude is the distance. A lot of times people will make the mistake, it's not a huge mistake, of going, oh, I'll measure from valley to peak, but that's actually double the amplitude. Does that make sense? Yeah. So, the answer to A is very simple. What is the answer to A? What's the physical meaning and value of the indicated interval in the diagram? Wavelength. What's the value of it? 6 meters. It's given in the question. So, and then B is what's the speed of waves on this string? Okay. Well, the speed would be the wavelength, 6 meters, multiplied by the frequency, 3 hertz. So 3 waves generated per second, 6 meters per wave. That means you're traveling 18 meters per second. Do you feel good about that? Does that make good sense? Okay, so number 2, I'm going to move on, but number 2 is just, it's phrased a little bit differently. It just shows a different representation of a wave. It's a sound wave though. So what makes, how come you can hear my voice? Well, I got the whole vocal cords and all the physical structures that their job is just to vibrate the air, just to cause vibrations. They're basically like doing this, but to the air. So they're going like this. They smack the air molecules, and that generates a wave. The wave travels through the air. It's a longitudinal wave. I'll show you one of those tomorrow. It's not a string, right? Because air is not a string. I'll give you a quick little drawing. The room is full of air molecules. And so what happens when you say like, there's like a drum here or something that's whacking the air molecules, it smashes them together and you get these regions of like dense, of high pressure. And if you keep doing that over and over again and then you observe the pattern, you'll have these like sort of spaced out regions. Does my drawing sort of make sense?
Yeah.
So you keep smacking the air and smacking the air. Every time you smack the air, you squish the air molecules together, and then they travel through space. And the waves travel through space. The molecules more or less stay put, kind of like how these dots stay put, right? So like when I talk, it's not so. A common misconception with like children is that, I don't know, like that when I talk to you, that the air molecules like from my mouth go into your ear, but that's obvious, that would be gross. So that's not the case, right? It's actually the air molecules next to my mouth got smacked, and then those smacked the ones next to them, and that chain reaction happened over and over again until eventually it got to your ear. And then the reverse process happened, that your eardrum got smacked, it got turned into an electrical signal, which then went to your brain, and your brain was like, "Oh, hey, I hear stuff." Right?
That's kind of crazy.
Yeah, it's crazy because it all started in my brain, electrical signal to the, I don't know, mouth muscles or whatever. I don't know how people talk. I don't really know how it works. Someone with vocal cords. Anyway, you're basically just like a speaker. Well, a speaker is very simpler. It's a magnetic. There's like a magnet and a coil. That coil gets a electrical a current through it, an oscillating current, and that oscillation is translated into physical oscillation, and that physical oscillation of the speaker is translated into physical oscillation of the air molecules, which is then translated into physical oscillation of your eardrum, which is then translated into electrical oscillation in your nerves, goes into Mr. Brain.
Mr. Brain now.
Right? You feels me?
Yep, it's yeah. It's a little trippy though. I just think it's just spring moving.
It's like, bro, we're all just vibration. Like, what if every atom was like its own universe and we were all like one singular energy just like flowing through time? Sorry. Just trying to my bad. Let's move on. Okay, so there's a couple questions in here that I think you'll figure them out for the most part. Like, I just want to briefly talk about 3 and 4. If you had these two, last thing was just that last question I was talking about. You answered the exact same way. That's all I was trying to show is that a sound wave through air is kind of complex if you really if you want to get into the details, but overall, you describe it using the exact same mathematics as you would for waves on a string. Anyway, moving on. Who has more energy, you think?
The right one?
Yeah, the bigger amplitude, right? Like, oh, which sound wave carries more energy? Like a little birdie going cheep, 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 or like a huge, a huge speaker, with massive amplitude, right? So the bigger amplitude, all the things being held equal, the bigger amplitude is going to carry more energy, and you don't have to like prove that mathematically. It just should make intuitive sense, I hope. And then on number 4, and then of B, who has the greater velocity? Well, if they're traveling on identical strings, and assuming that there's no reason to assume that the wavelengths or frequency, well, the wavelengths are definitely the same. Assuming the frequencies are the same, they'd have the same velocity. So all that means is like, in the simplest terms, if I whisper and then I shout, which one has the bigger amplitude? Whisper or shout? The shout, right? Does the shout travel faster? No. It's just that the oscillations involved are bigger. So back to this thing, this is a great analogy for everything. If I turn the amplitude up, now does that affect the speed that these peaks are moving It does not. It affects how fast these points are moving up and down. Sure, that's where the energy is. That's why you're having more energy. It has to travel faster to go up and down with the same frequency. But as far as the actual velocity of the wave, that's unaffected. Feeling's good? For 4, similar kind of question. Compare the two waves. They appear to have the same amplitude, but different frequencies and different periods. Like for example, if I call this A and this one B, how does B's frequency compare to A's? Count the number of oscillations. Twice as much, right? So A has a frequency of like, let's say this was 1 second. I mean, suppose it was 1 second of time. A completes 2 oscillations, so a frequency of 2 hertz, whereas B completes 4 oscillations, so a frequency of 4 hertz. So you can extend that. No matter what the time span was, wave B has double the frequency. Okay, what about the wavelength? Well, same kind of argument. He's got half the wavelength. That make sense? No? Confused? You're Gucci? Good, that's Poggers.
Yeah.
That's so Minecraft of you.
Okay.
How about the velocities? If they're on identical strings, they should have the same velocity. Make sense? And then who do you think carries more energy? This one might be this one's not obvious at all, but I don't know, anyone have a guess between these two? Same velocity, but one of them has a bigger frequency and a smaller wavelength.
Round 1.
It's this one. It's the second one. Because if you guys continue your physics education, you can sort of prove why that's true. But you're cramming more waves into a smaller space, so that's going to tend to have a bigger energy.
It's kind of like the molecule argument of like heat and stuff. It's kind of what I related to.
Yeah.
So if you get to move it more, yeah.
Hot, cold. Or like if you've ever heard of who's heard of like gamma rays, it's like gamma rays are just a form of light. What? Why they made what?
That's how they made the Hulk.
Oh, the Hulk. Yeah. So like in the spectrum of light, you know how there's like radio waves, and then as they get shorter, it's like here's radio waves, and there's like microwaves and stuff. And like what we see is like this tiny little right spectrum of something like 400 to 800 nanometers, give or take. And then gamma rays are the super short wavelength, super high frequency. Those will turn you into the Hulk. That's a fact. You will literally turn into the Hulk. Okay.
That's why radiation.
But I mean, that's okay.
What?
Get radiation sickness and stuff like
Oh,
that.
this is high from it.
Yeah, if these photons, these high frequency photons hit your cells, they can damage your DNA and give you bad boo boo.
You'll be fine.
So-
Sorry.
Well, it's fascinating. Your eyeballs, they get hit by this kind of light. They just don't detect it at all, but it gets hit by this kind of light, and that's how you see everything. Kind of neato, burrito.
It'd be so cool to try to imagine a new color.
What?
Like, if somebody imagined a new color, it'd be kind of fun to have.
I just did.
describe it.
Just a- Sorry, you got out.
That's the way.
Okay, so now we got time to talk a little bit about superposition of waves and beats. Okay, so we've talked about waves, right? Hopefully you got the main idea. The nice thing about waves, as far as like the real basics, is just look how simple that equation is. Very simple. the velocity of your waves is going to be determined by the medium, the thing that you're traveling in. Okay. Now that, of course, that's determined by a lot of things. I mean, you guys like, so some of you guys like to play music, right? For example, guitar string. What's one of the things that determines, say, the pitch of a guitar string?
Oscillating again.
The tightness, yeah, the tension. So,
Sound.
so on a guitar string, you have the tension, right? Because if you turn the little thingy, makes it more. If you turn the tension up, more tension increases the pitch. So, what determines this on a guitar string?
Like, like.
How what?
Like,
How hard you plug it?
Nope.
The
the,
scale length, or like where you are on the fretboard.
Yeah. First, it's the length of the string, right? So, like a bass has a way longer string, right?
Yeah.
Than like a violin. One of the reasons why a bass produces lower frequencies.
But also the bass things like this, that can silence.
Bridge cables.
Yeah.
Yep. So you have, but I'm saying there's multiple factors. There's the tension. So turning up the tension increases this, and thus would. So what I'm saying is, if you have a guitar string, we'll get into waves on stand. These are standing waves. We'll talk about these later. But the basic idea I wanted to discuss real quick was: here's your string. And like you said, if you put your finger on the fret, you've shortened the string. So you've tended to shorten this, which increases this, right? Then if you tighten the string, you actually increase the tension, and that's not obvious what that does exactly, but it increases this. It allows the waves to travel faster. If you go and play around with this thing, you'll see that if you turn the tension down on your string,
That's so cool.
so now the waves travel slower, but the same. You didn't change the frequency. That thing doesn't know about it, right? He doesn't know. So anyway, it's a lot of good musical connections here. We'll talk about the shape of standing waves on strings and how that's all, and standing waves in tubes too. So a standing wave in a tube, a sound wave in a tube would be like your flute or saxophone, things like that. Well, saxophone's interesting because you have to read, right? The reed
Yeah.
vibrates as well. But ultimately what you're hearing is that oscillation inside the tube. So, but same idea, longer tube. What happens if you have a long tube? Long tube means you have long wavelengths, which means low frequencies. And what determines the velocity? Well, that's the speed of sound in air. So things like the temperature, air pressure, things like that. So, anyway, how you guys? Have I lost you? Do you guys is this making sense at all?
yeah.
Sweet. Oh, and Griffin, by the way, how hard you pluck the string, that's basically going to determine your amplitude. So if you pluck it gently, maybe a small amplitude. If you pluck it really hard, bigger amplitude. But that's going to tend not to affect the wavelength of frequency. That's why you can play the same note loud or quiet, but you're not like changing the note by playing it harder.
Okay.
Okay, so last thing to talk about. Okay, so we have a little bit of time. That's okay with you, Julie.
Mhm.
You accept? You
I
accept?
do accept.
Okay, so number 8. This is a really simple idea with a fancy name. Superposition. Yeah, this is an incredibly simple idea, but it has big consequences. It has incredible consequences. In fact, I mean, all of like chemistry, quantum physics is all, I mean, it's largely based on this idea of superposition. Okay. Now this is the very simple example, which is suppose you had two waves. Suppose you had so 8A, the first one looks like, oh, I got a wave like this. And I got a wave like this. If those two waves were trying to occupy the same space, like say you were driving an oscillation on a string, and then you drove this oscillation, and then you also drove this oscillation at the same time in a way so that they synced up like this. What do you think the resulting wave is going to look like? No. They actually gonna add up. You add them. So this one has a height of 1, this one has a height of 2, so their sum is gonna have a height of 3.
Whoa.
Well, here's why what's louder, one person singing or 10 people singing? 10. Now, what's interesting though is your perception of sound is logarithmic. So having double the amplitude doesn't sound twice as loud. It's actually it's logarithmic. So you actually use like the multiply. You got to multiply the power by 10 to perceive a 10 decibel increase. So that's more of sound perception. That's not. I mean, it is physics, but we're not going to really cover that. Maybe we'll look at a chart later of like decibels. You guys have all heard of decibels, right?
Yeah.
It's kind of weird though. If you look it up, it's like 50 decibels is like your friend talking to you in the library, I think, and then like 100 decibels is like something that's super loud. I think like a jet taking off is like 120 decibels or something. You're like, what? Like a jet taking off is definitely way more than twice as loud as your friend talking to you. It's just that scale is nonlinear. So, okay, so you see what I'm doing here? See how they add up? Now there's really interesting stuff going on here because you go, well, if that's how it works, look at this one. The second one is the solid wave like, who's louder, the solid wave or the dotted wave? The solid wave has a bigger amplitude, right? But when you add them together, look what happens. What's 1 plus -2?
-1.
-1. +1, -1. And so your resulting wave that you draw is actually quieter than that big wave. You feel me? Okay, one more. What happens this? Who said cancely Wansley? Wow, what a legend. This one, if you look at it, for every single x value, the y values are opposites. That would be this is the perfect noise canceling headphones. Active noise canceling, at least. So they try to do that sometimes. They'll make this technology that detects waves coming in and tries to send waves that cancely Wansley those waves.
That's how like newer hearing protection for shooting works too. It'll cancel out pitches that are common with gunfire and above a certain volume level, but then just talking and stuff.
Yeah, it's like the electric ones. Yeah, I have those. They're pretty sweet.
Yeah,
You can actually crank on the side. You can increase the volume, so I can hear into Mr. Coleman's room. You can't. It's pretty interesting.
It's pretty sweet. Yeah, this idea, I'm sure it's involved. This is it's like those Bose noise. If you have the active noise canceling headphones, passive noise canceling is just there's a bunch of foam that absorbs the sound waves. Okay, that can get a certain amount, but obviously you're sitting on an airplane. You don't want to have these massive, things like you have an airfield. So they try to go, well, we'll keep them small, but have this little tiny device that tries to detect and then emit a cancely Wansley wave. But it's the principle of superposition.
So hypothetically, then if you really loud setting, but you have a whole bunch of sensors around you, a little bit farther out from you, they could send this signal to that noise canceling per se, and then they get out the correct signal. So hypothetically, you wouldn't hear anything then.
Yeah, if they work perfectly.
Yeah.
If you had the perfect technology that could perfectly detect what wave was coming in and then do an out of phase wave that cancels it out. Yeah, in theory, it can work perfectly. Obviously, there's limitations there. With your shooting headphones thing, I think the idea there is here's Mr. Earbly Weirbly, and then here's the protection. And then so it's mostly passive protection. It's a bunch of foam, but then there's a little microphone.
Yeah.
And then the microphone's connected to a speaker, and it has the electronics are just designed to be if a big wave comes in high amplitude, it just doesn't transmit the signal. But if it's a small amplitude wave, it does transmit the signal. So when your friend talks to you, it goes, oh, that's low decibels. I'm gonna send that signal to the ears. And if it's high decibels, it doesn't do anything. So it'll be interesting to look at exactly how they make that work. All the little, that's electrical engineering stuff. You know, how do you do that? How do you make a speaker only send the signal when it's a low amplitude signal? So, okay. Very last thing here, guys. So what if you had two traveling waves? Now we're almost done here, so I'll cover beats tomorrow. But here's the basic idea. This is your food for thought. Something to think about. What do you think would happen? I got two waves. Here's a wave. And here's a little guy. Sorry, I meant to actually have both the waves. Sorry. Here's two waves. They're going to travel toward each other. What's going to happen as they're passing through each other? That's the question. Superposition. That's superposition. Okay? Let's do it in slow motion. Like, watch this wave plus this wave. Look, if you add them together, right in the middle at least, that shouldn't surprise you too much, right? So let me pick a different pair of waves. How about, I'll post this online too. What if you had this wave and this wave? Like that. What if, I'm going to flip one of them over. Is it this one? Yeah, okay. Now what's going to happen? Now, of course, this triangular wave, you're like, well, what is that? You can't do that on a string, but you can do that in a conductor. You can make an electronic signal that's like a sawtooth wave or a square wave. So we'll look at the rest of these tomorrow. I got a square wave in there. Oop, there you go. So, but all it is, guys, the principle is really simple. You just add up the two functions when they cross. Cool beans? Lido burrito.